All right. So good evening, everyone. Tonight is class 2 of 2 on part 3 of Kepler's New Astronomy, which is as we already got into last week, it's a paradoxical and exciting part of this work. I will just say, and I know I emailed all of you, homework-wise was a little bit better last week. After that email I sent, got too late, and I would say incomplete. I must say incomplete submissions. And different people emailed me. I know there were, I was at this rehearsal also in New Jersey this weekend, and I think that interfered a little bit with the schedule, and there's some issues in LA. So anyhow, we should probably, not have some discussions. I think we'll have some discussions, maybe some of us from the basement also, with some of the helpers in the regions. Anyhow, just figure out how to make sure that this process works better. Because also seems like people are expressing, feeling a little bit, some people at least, sense of falling behind, maybe being stuck all the way back at the vicarious hypothesis. So anyhow, we should just work to figure that out, but people should really devote whatever time you can to figuring this out. I mean, Lynn continues to talk about the importance of Kepler and Kepler's discovery of the principle that organizes the solar system. So really do want to put a premium on doing this work. I would say that there were 5 homework questions, and at this point I'm going to cover the answers in the class. But what even the 2 people who submitted did not do, there were 2 essay questions, which I wanted to be a little bit more extensive. And I think they were both pretty good, and will give people a chance to write and think about some of the broader implications so far of this book. So I would ask people, those were listed at the end of the homework, if people can find time throughout the rest of the week to work on those, and for sure any other homeworks to go ahead and submit those. Those in particular, I wanted to see what people thought in terms of anyhow, some more general thoughts about the relevance and the polemics so far in the New Astronomy. So, but let's get right to it. One moment. I'm having a coffee delivered to me right now. That will help everything. Okay, let me take a sip. Alrighty. So, look over here. I'm going to do the same thing I did last week, where I made this sort of PowerPoint thing, and I'm going to, I'll share it with people afterwards. So, Session 2 here, if you read the chapter summaries, Kepler says chapter 32. So last week we covered chapters 22 to 31. And we dealt a lot with really Kepler treating for those chapters why the Earth is not going to be an exception to the physical principle which he wants to which he's in the process of discovering. A lot of it was, sort of really nitty-gritty. He's proving that the Earth has an eccentricity. And so we ended at chapter 31. There was a lot of calculations, etc. So chapter 32, the chapter summary, Kepler says, physicists, prick up your ears. And something like, now we're going to deal with something relevant to your domain. So if people, got a chance to do I know I read a little bit with Hector Villarreal yesterday. Some of these chapters, they're pretty fun, and they're different in some sense because he's really. This is, I think, where you really get the sense that he is. Whoops, let me switch back to myself here. That he is really developing. One, you get a sense of what's the state of physics. In terms of language, ideas at the time that he's working, and realize that it's quite different. I mean, this is like 400 years ago, and he's very playful in this part. He's making a lot of hypotheses, and a lot of the things that he says, today we could, you have to have a certain perspective on it, because you could say certain things he says, we know that they're not true today, but I mean, he is out there on his own developing this new theory of astronomy. But anyhow, so what I want to do is sort of review these chapters, 32 through 40. It's a lot of material, but we'll see how things go. But I'd like to get through it tonight. I guess what we can do is, just like last week, speak up if you have questions. Maybe I'll stop at certain points. But let's just get right to it. So I don't know if Cameron, you had mentioned last week, and this came up last week, and this is how he starts, chapter 32 actually, looking back at chapter 22 of the Mysterium. Did you get a chance to do that?
I didn't get a chance, no.
Okay. Well, I did.
Okay.
I found my Mysterium, and it's funny because it's very similar to chapter 32, chapter 22 of the Mysterium. One sec here. So just to review a little bit what he says in chapter 22 of the Mysterium, and again, this is what we dealt with last week, where he is already there in that work examining what could physically cause the need for a bisected eccentricity. And what he gets to there, and this is something that he's going to stick with and develop throughout the chapters that we're looking at, is the idea of the distance from the sun, the planet's distance from the sun, appears to be proportional to its speed. This is just a little quote. He says, "Let the whole universe be full of a spirit which whirls along any stars or comets it reaches, and that with the speed which is required by the distance from the sun." So it's funny. So this is in a sense actually what he argues again in chapter 32. Obviously, there's much more, there's much more background there. But interestingly, and this is really what we discussed last week, just to refresh in people's minds to review, what he does say in the Mysterium, and why he sort of, you could say, sets the thought aside for a little while, is that really until now, until these chapters here in part 3, is that he had doubts. He had doubts about this general statement about distance from the sun and speed. He had, and getting this, sort of being able in a sense to deduce this from the bisected eccentricity model. He had doubts at that time about the Earth, because it didn't seem like the Earth had any eccentricity at all. And so it was in the Mysterium that he said, okay, this is sort of seems to me generally what's happening, but it's a little bit of a problem that this doesn't work for the Earth. So I'll set this aside. And then, as we reviewed last week, different people, including Tycho Brahe, validated his, said he seemed like he was right. They also had concerns. And then what we spent the entire last class doing was actually proving this, was proving that the Earth has an eccentricity. It's small, but it allows him to go forward and make this more general physical proof. So that brings us to chapter 32. Now this chapter has a rather, and I had for these chapters encouraged people actually to read all of the chapters. Really a lot of them, many of the chapters in this section, some of them, in this group of chapters, there aren't actually animations until chapter 37. There's 37, 38, 39, and then a very thorough page on chapter 40, which is quite difficult. But anyhow, many of the chapters in this section, though, he is really just making these physical hypotheses. There's not many diagrams, so I didn't think it was too harsh to ask people to read everything. Chapter 32, there is a somewhat, intimidating-looking diagram, but it's a little more involved than the one that's in the Mysterium, but and I'm not going to go through it per se, but the point is he essentially comes to the same conclusion, and he's using again this model that we've seen with the equant, with the bisected eccentricity, and he goes through a certain kind of reasoning and says it appears that there's a proportionality between the speed of a planet and its distance from the sun. And again, he's using, by the end of this part, he's actually not going to have the equant in his model. But here, again, this is really akin to what he argues in the Mysterium. The equant model is being employed here, and he's saying even from this, we can develop some ideas about why it is that this works and what are some physical characteristics. What are some physical characteristics of what this is showing that we could use? So one of the best conclusions or hypotheses you can make from this bisected eccentricity model is this proportionality between relationship between the speed of a planet and its distance from the sun. So he's going to say this, we can get this from this model we've been using, and this is going to be my basis to then, really push forward with this idea of the sun as a power. Something he says here, and again, it's been a challenge for me to go back and try to really get a handle on all of this. What he says, this proportionality is, and again, keep in mind that this so-called model that he's using is, there's things about it that are incorrect, including its shape, etc. But he says, even given this model, this speed-distance relationship, it's true at aphelion and perihelion. It's slightly in error elsewhere. But I think he has ideas about he knows that what he's dealing with isn't a perfect model. So that's chapter 32, excuse me. And really, the next series of chapters are quite fun. And this is where he is really just theorizing and hypothesizing about, we could say, the true solar power. Okay. So again, please speak up if you have questions. Of course, if you didn't, do the homework or read any of these chapters, you're going to have more questions. That's a little bit different because, of course, you can't get everything from the classes. But by all means, speak up if something is very unclear. Otherwise, I'm gonna go ahead, move on. So chapter 33. What is the name of this chapter? One sec. I like his chapter titles. They're sort of fun. Chapter 32 was called "The Power That Moves the Planet in a Circle Diminishes with Removal from Its Source." Chapter 33. Oh, of course I don't have that page. Anyhow, it's something like the power, the sun is the power or something. So let's get this. So what he says in chapter 33, he's funny. He says, okay, so based on this distance law, it's a distance between what? It's a distance between two bodies. So he says this power, it has to lie in one of these bodies. The relationship is across a distance at either end of those, at either endpoint you have a body. So which body is it? And so the quote, I guess maybe this is the chapter name, "The power that moves the planets resides in the body of the sun." And as we know, and it's funny, it came up when I was reading with Hector yesterday, you sort of say, I mean, hasn't he said this like many times already? And he has. He has said this. He said it going back to part 1. When he dealt with mean and apparent sun. He said it going all the way back to the Mysterium. So it seems like he's already argued this explicitly and implicitly. So it sometimes comes across as funny when he states it as though he's stating it for the first time. And I think you have to really, again, you have to put yourself in his time. It also to us seems obvious. But at his time, nobody believed him. So as we know, he will assert something. He will then go and try and dispel any doubts people might have about why he's asserting it. He'll prove something like the beginning of part 3. He'll start his, you think that he's totally thrown out the mean sun completely, and then he starts part 3 and he's using it again. But it's because he's making another important point that will freak people out about the Earth. So he's just doing so much that's new. You really have to keep that in mind. And I think his view is, his argument, it keeps getting, the case that he's making is getting stronger and stronger. So after he makes another point, he'll come back and assert, it's the sun, but he doesn't want it to look like he's assumed anything. So he says some funny things in this chapter. I really think these chapters too, if you have thus far been at all intimidated by Kepler or anything, you can sort of fall in love with Kepler during these chapters because, just see how his mind works. So he says something funny. He says, okay, so you have a distance, this distance between the sun and the planet seems to have something to do with its speed. There's two bodies at either end, so which body is it? He says, well, I don't think it's really just in the planets. And he has this funny thing, and he says, they don't have wings, they don't have feet. They can't, he doesn't really think that the planets are doing anything on their own. They don't have wings, even if the planets had souls, they don't have wings or feet to propel themselves forward. He says something like that. And he says something else which I thought is pretty cool. He says, I didn't notice this until rereading it the other day, but he says, and this is, I guess, the other thing. He says, he admits that he's been arguing in an a posteriori way for the sun's directing role. That is, he's not assuming it. He's sort of showing you through very detailed work why you should be convinced of the apparent sun, and then now not just that the apparent sun is important geometrically, but that it's important as a physical power. So he says, I've argued in a posteriori way for the sun's directing role, but he says it's also the case that its overall worthiness would make a fine a priori argument, which he says would be just as good, which I thought was really neat. He said, and the fact that the sun makes everything grow. So I thought that was neat. He acknowledges that and that's what we've noticed. He's proving things through very detailed constructions, but he says, I think it is really just as good with the sun that you could make an a priori argument based on its overall worthiness that it has something to do with the planet's motions. I thought that was cool. So the first idea he puts forward here is that the sun's power is related to light. This is something that he studied in his optics. This is a book in English. I don't know if people have seen it. We had a copy in the basement. I'm not sure where it is now. Something he studied in his optics, which is, I think, 2 pieces. One piece that he keeps quoting in here, Astronomy pars optica, and another piece. And in there, it's really like a treatise on vision, physiology of vision, refraction, parallax. I think it was intended as something more specific for astronomical use, like parallax, but it became really a theory of vision. So he definitely had ideas about light. I mean, he had really worked on this. And I mean, one obvious thing to say is it's clear that the sun emits light. So it seems like makes sense to start with light. It's certainly something that the sun is emitting. That's sort of an obvious way to look at why he starts with it. But there's much more. There's much more to it, of course. So chapter 34. I'm going to move on now. That's the essence of chapter 33. Chapter 34 is more on the sun. He does continue to discuss the really what he's going to do now is he's actually going to sort of go back and forth between what he says, it's acting as an immaterial species. Whatever the sun is doing, he says it has that characteristic, which is he says it's also something an immaterial species, and in chapter 34 he says specifically a species like our soul. Now, I'm not going to try to describe that, but that's certainly an interesting idea. So what he introduces here and continues to do for the next couple chapters is sort of going back and forth. He's looking at light, how light functions, and also what he introduces here is magnetism. This is pretty fun, actually, and there was a homework question on this, which of course is a fun one. So let's see here. Okay, so chapter 34. He's saying it's an immaterial species. He says a species like our soul. But so the thing is, I mean, that's a very interesting way to put it. But how can we study this? And what he's really has to do is look for some analogies of things that he actually knows. The case of light. So the question is, and he's very clear, he doesn't think that light is the power. He doesn't think that light from the sun is moving the planets. But he's sort of asking the question, does it act like light? Now, I think one of the things that he's taking into account is he's clear that whatever this power is, it's spreading across very long distances. And he says something like, it obviously couldn't be an odor. It's not like an odor. Because an odor would dissipate. Odors can be very powerful, but they're certainly not going to span those kinds of distances unless it was something really, really stinky. But what he does have some understanding of is light, that light, you know, and of course we have Einstein and all these discoveries about light that came later. But he has an idea, well, light, you know, it seems to propagate instantaneously. It propagates very quickly in that sense. It's not easily, you know, impeded, I guess you could say. But it propagates in a very powerful way, and that's the point. And I think that's one of the reasons that he's looking at it here. Maybe the analogy with light is how this power from the sun, how this immaterial species, how it spreads, and how it's actually able to impact the planets. Because it certainly has to be more powerful. I mean, it's a silly example, but it's clearly not something like an odor. It has to span, you know, very vast distances. But again, as I said, he's clear that he doesn't think that its light is causing the motion. So again, keep in mind, he does not have an answer here. That's why these chapters, he's going back and forth. So he says, well, maybe light, and he specifically goes back and forth between light, and then he introduces the idea of magnetism. So light may be similar to, you know, to how maybe this species spreads, but how do we actually get the planets to move? And this is where he introduces the idea of the magnet. And the name of this chapter is "The Sun is a Magnetic Body and Rotates in His Space." Now, what's sort of cool, what's cool is that this is true. We can read that and say, yeah, that's cool. We know that to be true. That was not really so. That was not really so clear during his time, and ideas that people did have about that were very new. And I meant to look up when we. I meant to actually look more into this when we determine more specifically the rotation of the sun. But these things were very new. And what he's referring to specifically, so he says maybe the sun acts like a magnet. Now, aside from the fact that he's starting from the standpoint that he wants to figure out how the planets are moving, and this is a theory he thinks could work, William Gilbert was an Englishman who was doing work really it was new work at that time on magnetism. He wrote this tract called, I guess maybe that was in Latin, called De Magnete. And he didn't say the sun was a magnet, but he said that the Earth is a magnet. You know, something Kepler says, which again is not really right, is okay, so the Earth is a magnet. This can explain how the moon is attracted to it. This, of course, we know this is not quite true, but Kepler's in the process of discovering gravitation, so he's not going to say that he's not necessarily going to, you know, that would not have been obvious to him. But Gilbert was he figured out, you know, he was working on this theory that and this is not so simple, but the idea that the Earth has an iron magnetic core, and he also figured out, you know, he worked on how is it that compasses actually work. The idea that the Earth has a magnetic pole, and you can use a compass which will align itself parallel to that. So this is new work really being done then, that the Earth is magnetic. So it seems natural to Kepler, and of course that magnetism being something which has the power to draw things towards it, to repel them. So it's actually quite, it makes a lot of sense that Kepler would think that this might have something to do with how the sun is moving the planets. And what he describes is actually the idea, you know, he talks about, you know, thinking of the sun as being filled with magnetic filaments. And this is something that like he would have been able to get from Gilbert. But if you have the sun filled with magnetic filaments, if you have some of them which are parallel perhaps to the solar equator, then maybe, and we already know, right, this is something we know about compasses, you have the, you know, the magnetic pole of the Earth, and a compass needle, you know, will align itself parallel to that. So he could think, well, maybe these magnetic filaments parallel to the sun's equator could move a planet sort of in a path parallel to that, would have an ability to act on it. So it's quite interesting. The other thing he does discuss here, and he gives a couple ideas actually of, and also this is interestingly comes from, he's saying, well, okay, another thing might be that the sun, that one of the things contributing to the motion of the planets is that the sun is actually rotating, and he actually tries to figure out what the period of rotation would be. So there's a lot of exciting stuff in this chapter, and this idea, he'll continue to bring it up a little bit here, but you know, keep in mind we're on chapter 34. This idea of magnetism comes back in chapter 57. So if you thought you were close to being done, I'm done with this. Far from it. He's still got a lot of struggling to do here. So that's chapter 34. It is a very exciting chapter. And homework questions, a couple people did write, I didn't get a chance to really in detail review the homework, but a couple people responded to this. One of the homework questions was, you know, I've already discussed this a little bit, but what more do we know? What more do we know about the magnetic characteristics of the sun or of the Earth than Kepler knew at his time? So one of the answers was, and this is just fun because this is where, you know, this relates to, you know, stuff we've talked about in the basement more recently, things that, you know, we're really, what's exciting is, you know, during Kepler's period, we were starting to figure some of this out, like figuring out the Earth's magnetic character. And there's no solid answer now. We're still figuring out more about the sun's magnetic character and the Earth's magnetic character. So something I put was, you know, a possible answer to the homework is something that we know that Kepler didn't really know about, was sunspots. Oh, these were first observed, interestingly, I didn't know this, so I looked it up. They were observed telescopically in 1610. People know when the New Astronomy is written? Pop quiz. Anyone know the year of publication of the New Astronomy? All right, 1609. So that's pretty cool. So he's doing this. He's talking about the sun having a magnetic character, and sunspots were observed telescopically for the first time in 1610 by David Fabricius, who was actually Kepler's friend. And he published his results on this in 1611. Now, I don't think just observing them, I don't think David Fabricius or people then knew what we now know, which that sunspots are regions of intense magnetic activity on the sun. So that's actually pretty cool. Another answer could have been that we know more about the heliosphere. This is this vast region. We now know it's not just you know, question of the sun or the Earth as bodies being magnetic, but there is this entire sort of field of influence of the solar magnetic field interacting with the Earth magnetic field. And this is called the heliosphere. This is a picture of it. I'm sure people have seen this. Sort of looks like a, you know, woman's skirt or something, a very flowy skirt. Yeah, and you can see, if people can see that, you have the sun at the center and you have the planets going all the way out to the outer planets, and it's, you know, it's a certain representation of what the shape of this this field of influence of the sun's, really the sun's electromagnetic, magnetic environment spreads in that way. So it's quite interesting. I'm thinking if Kepler saw that, he might think, yes, it is magnetism. Anyhow, so it was sort of fun. I just had those answers in there for fun and that question in there for fun. So the next couple of chapters, he is going to deal with some things that they're not really, you know, he even says the chapter 36, he sort of wastes some time. But he's going to put forward some more ideas about accounting for the planet's motion, and he has to not just account for its motion, he has to account for the fact that there's a changing speed, that it slows down, it's not constant. So he has to account for this. He has to account for the change in speed, and not just the motion, but the slowing down. So chapter 35 is on, and again, he brings something up here that it's not true, but it's not doesn't really explain much in terms of what's moving the planets, but it's interesting. So it's on occultations. Now this was a question, actually this was a homework question. What is an occultation? The homework question was, can you give a historic example of an occultation? So an occultation is when, like this. Here, I did my homework. This is an occultation event. Oops. Can't actually, oh there. It's an occultation event. The occultation of Saturnian moons. So you can probably tell from looking at this that occultation means a body which is blocking another body, passing behind it or passing in front of it. So these are two Saturnian moons, Dione and Rhea. I don't know the exact date, but it was seen by the Cassini-Huygens mission, so that gives you an idea. So this is what he's looking at here, and he's asking himself this question. He's entertaining looking at occultations to try to explain why it is that maybe does this account for this slowing down of the planets. So the question is the species which is emanating from the sun, is it affected? Right, it's trying, you know, let's say it's trying to act on a planet. Is it affected, or is it affected? Is it attenuated? In terms of next chapter, and also a homework question. But is it affected when an intermediate body passes in between? If you have the sun and Mars, and let's say Earth is in between, like at an opposition. You have Sun, Earth, Mars. Does the fact that Earth is in between them, does it actually does that actually cause Mars to slow down? Does it lessen the strength of the power of the sun upon Mars? And he has something which I thought was sort of funny. He says that, hey, maybe this is why God gave the planets relative inclinations, so that wouldn't happen all the time. Which just gives you a sense of how he's reasoning here. The thing is, in this part, he doesn't actually, you know, and it's certainly not the most important chapter, but he's really, again, he also wants to make sure that he's looking at everything. So he doesn't consider this for too long. You know, it's even the case as well, that's not even really, if this power acted like light, light isn't, basically, even to answer it the way he's posing it, you would have to know more about what these bodies are made of. Like, light isn't really blocked by bodies; it's blocked by opacity. So anyhow, he can't really answer it. The way that he's posed it, and the fact that he said maybe the species acts like light, he can't really answer that question. But anyhow, it's just part of his argument here. And the point is that he has to explain why the power appears to be weaker at different points in the orbit. That's why he's even looking at it. So that's chapter 35 on occultations. Or the name of the chapter is Whether the Motion from the Sun, like its light, is subject to privation in the planets through occultations. So next chapter, chapter 36, by what measure the motive power from the sun is attenuated as it spreads through the world. So this was a homework question. You know, I just wanted to check, make sure people read these chapters. So this question wasn't really that hard, but so what is it? What does he mean? What is attenuation? Let's see here. So attenuation is basically the loss of intensity. So he's saying, how does the power of the sun lose intensity or attenuate as it spreads itself out through the world? So again, attenuation is it's a physics term today. Attenuation is loss of intensity of a flux through a medium. Light and sound are attenuated by water. There are also other examples you could have given as an answer. So again, I'm actually not, because we got some serious chapters coming up, like chapter 40, big old chapter 40. So I'm not going to spend too much time on this, and I'm not going to spend too much time on this chapter. Kepler himself says in this chapter, I'm having a good laugh at my pathetic worrying over so much hot air. So the diagram from this chapter, and these chapters here, again, there's not many diagrams. There are like maybe a couple sort of funny ones like this. I took a picture of it here, where you can see the sun there. He made it really look like a little sun. And you see he's looking at sort of the area of sort of extending from it a surface or an area, and looking at, you know, how much of the immaterial species considered in that way, and how much of it gets to point beta and point, oh god, gamma, I guess. So he sort of considers it, and he's sort of looking at it in a pretty geometrical way. And again, he ends up saying that, you know, looking at trying to figure out, okay, well, given a certain distance, how much less, really like considering these as areas in a sense, how much less of the species is at beta versus gamma. But he doesn't really conclude anything too decisive here. And the end of this chapter, though, he brings up the thing which he's brought up before. He sort of says, okay, well, hold on, I have to really reconsider. You know, he really reaffirms the idea that it's important to look at the sun, to think of this, whether this power from the sun comes from its rotation. The role of solar rotation in producing the planet's speed in its specific location, versus just the idea of a static body which is emanating the species. And what he gets into at the end is he says he entertains a lot of ideas. He'll put forward a theory for how the power would work, and then say, well, maybe it's not right for this or that reason. And he says, I have to account for the fact that the planets, there are relative inclinations, but the planets are generally confined to a zodiacal region, right? They're in a relatively narrow band. So he says he sort of also in doing this reasoning figures out things he has to make sure he accounts for. He says, okay, I have to actually account for the fact that the planets don't just move it any which way, that they're generally confined to this region. And he ends up sort of reasserting in this chapter that, well, this is another reason why maybe it's important to look at solar rotation, because if that has something to do with how the power is emanating, that might make sense. If the sun is rotating, if the sun is rotating in this kind of fashion, that might have something to do with the fact why the planets are confined to a band, proximate to the direction and the direction that the sun is rotating, and in that direction. So that's what he that's what he gets to at the end of this chapter. He says, okay, I have to keep this in mind still. Solar rotation. Maybe this maybe this has something to do with it. Maybe this will help explain why the planets are not flying all over the place. So then the next chapter is also a fun chapter. And it might seem like he's sort of jumping all over the place here, but he's creating new astronomy. So he's put forward a couple hypotheses: light, magnetism, entertains some wilder ideas, maybe occultations. Does this block whatever the species is? So now he's going to say, okay, well, let's look again at, and again, part of his insight into magnetism was because he actually had, that was something that we actually knew about the Earth. So now he's going to say, okay, well, so now I'm going to reason in a different way. Let's actually look at two bodies that because what he's looking at is the relationship between the sun as a body and the planets, and figuring that out really, he doesn't have anything. He's creating something totally new. Then we do know a little bit more, and let's look a little bit at two bodies that maybe it's easier to study, or we know more about, and where one is clearly moving the other, and this is the Earth and the Moon. So the next chapter is on the Moon, chapter 37. And it's also sort of a funny chapter because he asserts something at the beginning that he doesn't really stick with. The chapter is just called How the Power That Moving the Moon Functions, or something. So this is a picture of this little diagram that he has in this chapter. And this is the first chapter in this series of chapters we're looking at tonight, where he has where there are animations on the website. So he says, okay, so he has this diagram. The sun is at S. Then you see he has the different planets. He has Mercury. He has Venus, M, V. Mars is at P, that little star shape, and then the Earth. So he has the Earth. The Earth might be point T, and then you see he has this little circle surrounding the Earth, and that's tracing out the path of the Moon. And you'll see he even traces it out to the right there. He traces out the path that the Moon makes. So he sort of goes through, well, how, what's the relationship between the Earth and the Moon? It's very clear the Earth moves the moon. He says it's like a ball and a chain. You know, it's like attached to us, like we have this chain. Jason has this, and he tries to look at around this circle, and he calls this this circle, tracing out CLOF, this circle. He calls the diameter of this circle the diameter of power. And he's looking at, sort of based on some of his ideas, does the moon go faster, for example, at O, or C, or L, or F? And in terms of what he says about that, I'm not going to really get into it because he doesn't end up concluding that it's that important. In terms of some of that, Jason, Jason has a little link to a video on the website showing those Disney World teacups. Sort of an analogy maybe between the moon, between them and the moon's motion. But ultimately, what he says here is he says this diameter of power, which is really this, again, that it's another distance. He's looking at a distance and trying to figure out a power acting across that distance between the Earth and the moon. What he says in this chapter is that ultimately the diameter of power has its seat in the sun. And that's how he concludes this chapter. He says, nevertheless, it is the sun which is the principal director. So although the Earth is moving the moon, the sun is moving the Earth. So that's, he doesn't really, it's a funny little chapter. He doesn't, that's how he concludes it. Nevertheless, it's the sun which is the principal director. Okay. So we're getting to the tough part here. Take a little coffee break. Okay, so the next chapter, he goes back to actually, and this is what he's doing here, he goes back to something he brought up at the very beginning of this series of chapters, in chapter, I think it was chapter 33, where he says, okay, I'm looking at a proportionality, a relationship between speed of a planet and its distance from the sun. And he says this thing, he says, okay, so he goes through some reasoning and says, well, okay, so if it has something to do with this distance, and it's there's a body at either end of the distance, it has to be, whatever this power is should originate from one or the other body. So we've been discussing, mostly, he says, well, really we should look at the sun, because the Earth doesn't have wings and it doesn't have feet. But he actually sort of entertains that a little bit in this chapter. This chapter is on something called vis and Sita, which really means an innate force, a force proper to the planet, or proper to the Earth, or proper to Mars. Now, for what it's worth, just because I wasn't, wasn't a term I knew from Leibniz or anything. This is described in at least one location I found. This is described as inertia, which of course is that. It's it would be it would be, if you're looking at the sun and the Earth, some kind of change in speed of the Earth or Mars or whatever planet, which comes from itself, that it's active in some way, but in a funny sort of passive way, in a much less active way than the sun. But the point is, in this chapter, he's considering the role that the planet itself is playing in determining the path. Although, you know, he's certainly not at this point entertaining the idea that it's you're not throwing out the sun, but he's saying, well, maybe it's mixed. Maybe in terms of describing the actual path that the orbit takes, maybe there's a mixing of this power from the sun and something which is actually that the Earth is not completely passive. And what he sort of settles on here is a combined cause, and he uses this funny, he brings in some characters here, which are these little ferrymen, literally men on little boats with oars or with paddles. So what he said, he settles on the sort of combined cause here of the sun, which you could say is this rapid torrent, right, of water. So that being the sun's role, and the Earth, as though the Earth were carrying a little ferryman who had an oar, who had a paddle. So clearly the dominant power there is the sun, is the rapid torrent of water. But thinking of, and again, this is pure analogy, that the Earth is actively playing some role here in determining its path, in the same sense as a ferryman who's sticking his paddle in the water. Surely, if there weren't any water there, he wouldn't be going anywhere. But he can, you know, by placing his paddle in a certain way, he can resist the force of the torrent in a certain way and have something to do with determining his own path. And he introduces the idea that, well, what would guide these ferrymen? Maybe it's the perception of the solar diameter. Maybe that's something that, and not literally a ferryman, but again, he's using an analogy here. Maybe this is the thing which guides the ferryman in terms of, or is determining what he might be doing. And Jason has a little page on this on the website, and this gives you a sense of the idea. He actually he has a picture of a specific ferry, and it's a specific kind of ferry, and he references a Wikipedia page actually on reaction ferries, and that's really the point. It's like that what's determining the motion of the ferry or the boat or whatever, it's working with the water, but it's not completely passive. You know, you have whether you have ferrymen with paddles, or in this case Jason reference was a little bit different, but it was where the actual motion that the boat takes has something to do with, you know, that where it is in some fashion determining its motion. Okay. Okay. About 8 o'clock, so this looks good because next couple of chapters are going to take some time. All right. So the next chapter, so the name of that chapter was 38, was Besides the common motive force of the sun, the planets are endowed with an inherent force, vis in Sita, and the motion of each of them is compounded of two causes. Okay. So the next chapter is fun, and Jason has some fun stuff on the website on this. It's by what path and by what means do the powers seated in the planets need to move them in order to produce a planetary orbit through the ethereal air that is circular, as it is commonly thought to be. So he's, of course, found, again, this is another kind of reasoning. You really see what a playful mind he has in these chapters, I think. But this part, he's going to bring back something, again, which he sort of already said he doesn't think is true, which is a circular orbit. But Okay, so he's thrown a lot of concepts out there, how this power from the sun could work, how it could cause the motions of the planets. But ultimately, what he has to do here, you know, he's not just, he can't just put forward these theories. He has to actually, right? He wants to take control of, and revolutionize astronomy, which means he has to put forward a physical theory that's actually going to, it has to work. It has to actually allow him to make forecasts of where planets are going to be. So he sort of returns to this in chapter 39. And he, interestingly, is, what he looks at here is how difficult it is to produce, to physically produce, as opposed to just, assuming, that like these guys, assuming that, right, this simple eccentric, the circular orbit is just there, and you're just sort of like fitting things into it. Saying, well, how physically do you produce circular, circular motion? In terms of what he's going to show, it's going to show, I mean, it seems simple, right? Circles. What he's going to get into in terms of the shape of the orbit is much more complicated than that. But he asks, how does a planet's motion on a circular eccentric, how is that physically produced? And he introduces, and I'm not going to get into all of them, he says that there are specifically 5 physical absurdities that you run into when you try to do this. One of the things, I'll just say one of the things this includes, these are things he's brought up before actually, because he's already sort of introduced this idea of ridiculous things that are required when you have circular orbits or points of uniform motion, in a Kuzanisha kind of way. But he said, in addition to, not going to get through all of them because we really need to devote some time to chapter 40, but in addition to just this idea, which he absolutely hates, of something paying attention to a point where there's nothing there, he ends up saying you need to produce a circular orbit, you need he brings back motion on an epicycle, really just looking at how physically do you produce these models that these other guys used. And he says you end up needing to have the planet not just moving on an epicycle, but sort of reciprocating up and down, and the speed at which it does that is really not clearly determined by anything. So he says, anyhow, so he introduces 5 physical absurdities that are that result when you try to physically explain how you get a simple circular orbit. And he says, just a quote from this chapter, he says, oops, he says, the preconceived notion of the perfectly, so he's not even done with this. This is part of why this is funny. And it's also just funny language. He says, the preconceived notion of the perfectly circular planetary orbit, and also to some extent that of the control of the reciprocation, what I was mentioning, reciprocation on an epicycle, by a mind, will shortly be torn to shreds on geometrical grounds in chapter 44. So people can look forward to that. And again, so he's faced here, and we'll look briefly because Jason sort of really he does a fun pedagogical on this. But just keep in mind that he's faced here, and he's going to continue to face throughout part 4 the challenge of approaching geometry from physics. He has to create a desired shape, a shape of the orbit that works, which truly describes and forecasts the planet's motion, but his criteria is that there has to be a true physical cause. And his predecessors and contemporaries, they did not care. And if you haven't figured it out already, this is not easy, what he's trying to do. But so now for the remainder of what we're going to do here, we're going to look at the website, including for this chapter. One sec. So chapter 39, Jason just has some fun stuff here. He actually looks at how difficult it is to, people can look at this on your own, but just so people know what's there, he looks at how difficult it is to create a straight line. And he actually looks at devices people had to develop for, automobiles. You have pistons that need to, if they're not going to produce wear and tear, they have to take a very straight path. So ultimately, that involves figuring out physically how to produce straight line action. So Jason just has some examples here of people who tried to figure out how to do this. He has a couple little. Here's a couple constructions. Oops. Shh. What is that? Strange sounds. Anyhow, he has all these different constructions looking at
that was referral from LA.
I didn't hear who that was, but it's okay. Stop. So yeah, he looks at this guy, Poisselier, different ways that people tried to create straight line motion in the context of how to have the straight path of a piston. And yeah, this is a very good page. I suggest people read through it. It's very pedagogical. And he goes through these physical absurdities. And yeah, I'd recommend people check that out. I'm not going to go through it. This is the little image he has of reciprocation along the epicycle. The little red dot. This is something that, it says to describe the shape of the orbit, you have to figure out how to do this. But the question is, there's really nothing reasonable that this little red point is paying attention to determine its the way in which it's reciprocating on the epicycle. So anyhow, people can check that out. So now we're going to move on to the Big Kahuna, chapter 40. So we can take a little pause. Maybe people, these past chapters we've been discussing so far, they aren't necessarily, you may not necessarily have questions about them, and as I've said, the point with them is not necessarily to figure out if Kepler is right or wrong in a given chapter. But if people have questions or anything to say so far, go ahead. Otherwise, we're going to move on to chapter 40. And I'd like to probably spend, I don't know, we'll see how long it takes. May not take too long, but yeah, I want to leave like 15, 20 minutes. We have this call.
Can you hear me?
Yeah.
Did you say at the end of chapter 37 that the moon gets determined by the sun and not the earth?
He just says that, it's not as though, of course, the earth is moving the moon, but he sort of just ends basically saying that to look for a strict analogy between how the earth moves the moon with what he's trying to figure out the sun, it's not really important because, and even ultimately, the earth isn't moving the moon independent of the fact that the earth is being moved by the sun. that's sort of his, that's what he says. He says, nevertheless, it is the sun which either immediately or through the faculty which governs the Earth's annual motion, it is the sun which is the principal director of the motion which the Earth confers upon the moon. So that's what he says. He is acknowledging that it, you know, we are moving the moon, but that's not really the problem he's trying to figure out. And he doesn't get any real great insights in what he does in that chapter to the sun's power. Oops, forgot to click back on myself. Anyhow, so let's deal with chapter 40, and I think chapter 40 is an important chapter. I think Jason is going to be doing the classes on part 4, and I talked to him a little bit. I think he might end up revisiting maybe some of what's in chapter 40, but I definitely want to give people the best idea I can of what's in there. And the good thing is, and why I don't need to go through absolutely everything, I will say the website page on chapter 40 is very thorough, and I really want to encourage people to work through it. The other pages, 37, 38, 39 are good. 40 is really crucial, and you really want to understand what he's doing there. So I'm going to go through it using the website and just my own, what I figured out. So chapter 40, this is where Kepler, he goes back really to what he had in chapter 32, which is, and what he's been trying to figure out, the physical reason for it. He hasn't necessarily, he doesn't have an answer yet. But starting from what he said he figured out in chapter 32, which is this correspondence between speed and distance, he's going to actually try to start applying this now and figuring out to what extent, based on that, and he doesn't want to accept that just as like a mathematical law. He wants to figure out the physical cause, but he's going to bring that back, the idea of speed and distance determined by the sun, and he's actually going to try to figure out if, given this, he can begin to try to make forecasts. Can he figure out the elapsed time on a portion of the orbit? Can he maybe start to, what he needs to be able to do, forecast where a planet's going to be? Does what he's pretty confident about, this distance law, does this enable him to do that? And he gets to the idea that it does, that there is that he can actually take this further. So this is chapter 40. Now, I'll just show people the notes here. Okay. And there were a couple homework questions on chapter 40. Now, the name of chapter 40, this is one of the homework questions, which is why what Kepler does in chapter 40, why does he say it's imperfect? Now, that's the name of the chapter, states explicitly that he thinks what he's doing here is imperfect. Chapter 40 is called an imperfect method for computing the equations from the physical hypothesis, which nonetheless suffices for the theory of the sun or the earth. So he has been really, part 3, he's going to go back to Mars. He is, as he said, part 3, he is dealing with the second inequality. He is dealing with Earth. So when he's using any, just to be clear, the constructions and diagrams that he has in this part, you know, when you're looking at any construction of an orbit that he has, it is of Earth. And so that's important to know. In Chapter 40, he is still looking at the Earth's orbit, of course, trying to make a more general proof. So sort of armed with this idea about distances and speed, he asks himself whether he could add up a series of distances and make them equivalent or at least proportional. He knows that they're not equivalent, and that's part of the point. Whether he could add up a series of distances from the sun to the Earth, and actually get out of that an area which would correspond, you know, correspond to an arc, correspond to an area, and an elapsed time associated with that. And he says that his attempt to do this is imperfect. Why? Because he knows that he has the idea that the planet's speed and its distance is always changing. But he doesn't have infinite distances, of course. He's not able to. What he ends up doing is actually trying to use like the idea of dividing the orbit up into 360 pieces. That certainly is nowhere near, you know, the infinitesimal, but it's really the best he can do within reason. So he knows he doesn't have infinite distances. He says, you know, I know that I can't traverse the infinite, but I want to proceed with the idea that a given number of distances in a sector of the orbit, that I'm going to proceed with the hypothesis that I could actually say that those correspond to an area, and then that swept out area could actually correspond to time, elapsed time in the orbit. So his answer is going to be imperfect. He does know that, and really, this is, you know, where it's not. It's one of the ways where you can see where Kepler's work it begs the calculus. He needs it, but he's also the actual work that he's doing. He requires it, but he's also sort of making a physical case for why you need that, which is something where he could actually analyze constant change. He knows he's not doing that. So just before getting into the actual point here, just some of the basics. I had a homework question, which was for people to. So now we lucked out past couple chapters. We didn't have to look at orbits too much. Now we're going to get back into this, and it's the meat of the work of part 4. So the homework question was to show, because this is just vocabulary that he uses here and he's going to keep using, the eccentric anomaly, the equated anomaly, and the mean anomaly. So the answer to this homework problem is actually on the website. People should look at it. So part 3, excuse me. Part 3, anomalies. Okay, so this red pie area from the center sweeping out an arc on the orbit is the eccentric anomaly. I should have asked the homework question differently, but it's fine because you'll need to know this too. The equated anomaly is an angle. It's an angle swept out from the sun between, I guess, the line of apsides and the location of the planet. The physical equation, anyhow, the mean anomaly is the eccentric anomaly, this red pie slice, plus this triangle here between the sun and the center and the planet, called the physical equation. And when you add this area, the green area, the physical equation, to the eccentric anomaly, you get what's called the mean anomaly. And this is an approximation for elapsed time. You see it's being swept out. There's no equant here. This is being swept out, and that's what you'll notice in Chapter 40. he actually, the equant is not there anymore, which is cool. Anyhow, so that's the homework question. Some vocabulary that we're definitely going to need as we move forward. Homework was just to show that. So something he actually does here, and again, I'm going to have, you know, I want to get the main points. Something he actually does here, and you can check it out on, it's on page 422. He tests. So the mean anomaly, you know, it's the total mean anomaly. The largest value it could have would be 360. It would be sweeping out the entire area of an orbit. And they say that that value would be 360 degrees. That would correspond to basically like the periodic time of a planet. You know, when it comes back to the same point, you'd say it's after 360 degrees of mean anomaly, sort of the unit for a planet. And that's an area swept out being traced from the sun. So what he actually does here is he tests, he actually analyzes the orbit now as an area. So he does a geometrical analysis of the orbit he set up as an area. Where the full orbit would be a mean anomaly of 360 degrees. And he tests what he gets for that. He tests this new model of the orbit that he has in Chapter 40, which doesn't have an equant. He tests it against the equant model orbit. And he gets a value for a little area in the orbit. I'll show you. So this is the model that he's dealing with here. This one. See, there's no equant. So anyhow, he says he analyzes this little area, ABO, this little triangle. And he figures out what area that is as an area, as a portion of 360 degrees in this model, and he compares that area of that little triangle to what it would be in the equant model. And he says it's almost the same. He says it's 33 seconds off. This is a value he gets on page 422. So he says, okay, I can now basically proceed with not using this other planetary model anymore. I'm going to use this model which doesn't have an equant. And Jason actually has a fun thing quantifying this discrepancy in something else people can definitely read is Jason's wrap-up, Part 3 wrap-up. He's got some fun stuff there, but he actually shows, pretty sure that, yeah, he shows the discrepancy between the equant model and his distance corresponding to area corresponding to time model. So you can see the equant one, the path it traces the planet in red, the other one in blue. And he shows how as you zoom out, this actually becomes significant. Well, as you zoom, he shows that as you zoom out, it can become imperceptible. As you zoom, rather the opposite. As you zoom in, it becomes significant. So he starts chapter 40, and then it actually gets much more complicated than that. But he starts chapter 40 basically saying, I'm vindicated in using this new model of the orbit. Oops. Yes. Okay. So then the question is, well, sort of how is he approaching this? How is he even approaching? But he acknowledges that it's not perfect, and that his point is that there is a little discrepancy. So sort of what he does for the rest of the chapter is he's trying to sort of correct for and figure out the characteristics of this new orbital model that he has. So how does he even really come up with this idea of the distances corresponding to an area? How does he come up with that? He comes up with it because this is something that Archimedes did. Archimedes did this with a circle. I thought this was on here. Yeah, look. See, I'm just really going to use the website here. So Archimedes said, I can figure out the area of a circle by approximating it with a series of triangles. So this is a construction on the left here that Archimedes did. And doubling the area of each of those triangles, basically giving you a rectangle. So saying, okay, this is a certain way in which he approximated the area of a circle with an area of a rectangle. It's like squaring the circle. So Kepler uses that. He says, okay, I'm going to do something similar here. But of course, he's not dealing with a simple, he has an eccentricity here, and the area that he's sweeping out is from the sun. It's not from the center. The triangles Archimedes was using were from the center. So this gives him a shape which is different. It gives him a shape called a conchoid, which is this shape on the right here. So this is very nice. So this is showing actually what Kepler, it's dividing using a series of distances, and I think he had more distances than this, saying that they're approximate to the sides of triangle, a series of triangles, and mapping it similar to Archimedes and creating this shape, which is not a rectangle, because we're sweeping out from the sun, not from the center. And you create this funny shape called a conchoid. So he says this is actually the area, not this rectangle that Archimedes got. This is the area that he is dealing with, and what he needs to be able to do is really to analyze that area and to analyze portions of that area, because those are supposed to correspond to elapsed time. And he ends up sort of figuring out that even this conchoid is a little bit of a problem. It's a solution, but in terms of being able to analyze it, it's a bit of a problem. And so I'm actually going to end just going through this. So the conchoid, it's a solution, and it is also presents some new problems. So again, we're looking at the Earth here. The eccentricity is small, but in the next chapter we have to treat Mars. So it's going to be, it doesn't really matter if for the Earth, whatever errors we have here, if they're small, because we need to treat Mars in part 4. So he comes up with this funny thing that it seems like the area that that this conchoid represents is greater than the area that Archimedes would get, than the area of the circle, just because the lengths he's taking are from the sun and not from the center. So this already seems a little bit funny. How can you see that this is sort of the case? You can see already at the quadrants, so already in my little diagram, and there's something on this on the webpage. Already at E, the distance, so let's say you're sweeping out from the top. Already at big E, the distances from the sun are still longer than the distances from the center. And you're already like halfway done sweeping out. So it already seems like this is going to be a larger area, which doesn't seem to quite make sense. And of course it switches at a certain point. This point here, they would be equal, and then the distances from the sun would be less. But Kepler says it actually seems like this area is larger. And there's more on this on the website. We're looking at the same thing. comparison of these distances at the quadrants, that the distances from the sun are longer. And then it does switch. But there ends up being a bit of a problem, he realizes, with what he was doing with this conchoid, which is it's not quite similar to what Archimedes was doing. So he not only in this chapter has a conchoid, he has another conchoid. See this. The first conchoid that he develops is the conchoid, it's this larger one with points C, G, H, E, I, K, A, with its endpoints at A. That's the first one that he develops. Then he corrects for it because he realizes that there's a problem with it. What he realizes is that the triangles from the center, like the triangles that Archimedes was sweeping out, these little, you can imagine them as infinitesimal triangles, or even just you can think of the distances that you're using to create these triangles. In what Archimedes is doing, the distances are intersecting the circle at right angles. And that's important just in terms of the geometry of then creating that rectangle. The fact that they're intersecting the circle at right angles. But Kepler is taking distances from the sun, so they're not intersecting the circle at right angles. So he doesn't simply, that rectangular shape Archimedes got is composed of, right, a series of, you know, base times height of these triangles times 2. But the distances Kepler is using, the distance from the sun to the circumference, to the orbit, it's not really it's not base times height. This is not really the height of the triangle because it's not intersecting the orbit at 90 degrees. I'll say that much about it. And again, I know this is probably a little bit difficult to follow and it's nitty-gritty, but I want to just have it all out there and people can go back and try to figure it out. I'm just trying to give people a sense of why on earth he has one conchoid, why does he have a second conchoid? He realizes that the shape that he had for this first conchoid is not really true because the triangles that he's using aren't, they're somewhat incorrect. So he makes a second conchoid correcting for this, where he actually finds out what the actual heights of those triangles would be. He does it using, I'll just say he does it using this construction here, which is a construction, it's actually sort of a method that he'll use more in part 4. I think he finds out that the actual AH is not the height of the triangle, RH is. RH intersecting the circle at 90 degrees. So he says, okay, that changes what these, that changes what the heights are of the conchoid. So the second conchoid he makes, its endpoints are at Q, R, S, and L, and these Greek letters. So it's slightly smaller, but it's more accurate, and you're more able then to actually make divisions of it. Equal divisions of it would actually tell you something, whereas his other one was a little bit inaccurate, so it wouldn't have worked. Anyhow, that's about what I'm going to say about it. And he ends up, he poses a problem for future geometers. And this is not the last and only time that this is going to come up again in part 4, where Kepler's, this is a much more minor one actually, relatively speaking. He says, I need future geometers to help me figure out the area between these two conchoids. And again, keep in mind, what does the area represent? He's going with the idea that distance corresponded to area corresponded to time. So he got an area that he thought corresponded to the periodic time of the orbit, and he would like to be able to make divisions equal divisions of that area that could give him a sense of an elapsed time. So that's why he cares about this particular problem of the shape of the conchoid at the end of chapter 40. So that's what I'm going to say about that. People should work through the chapter 40 page. It's a little bit challenging and funny to figure out this thing with the conchoid. But ultimately, we're moving on to bigger and better things. he is going to use this, but he's that's the important thing, is to realize it's not just a funny geometry thing. It's the fact that he's struggling at this point to figure out how he can actually quantify the elapsed time based on this new model he's developed, which in chapter 40 there is no equant. He's just using the sun. He's meting out elapsed times from the sun, not from an equant. So it's totally new, and he's struggling with how to work with that and how to be able to analyze it. So this is the point. I'm going to end here. It's can he forecast where a planet's going to be according to his theory? And this is really why we're looking at this in the first place. It's physical forecasting. This is how Lynn brought this up. This is why we even started working on this. Physical economic forecasting. Can Kepler make a physical forecast of the path of a planet? Not statistical, not mathematical, not geometrical. Same with what Lynn does in economic forecasting. That's why he had us look at this. That's why we're looking at this. So there's going to be much, much more of this in part 4. And I've given you a little taste of part 3, a little taste of chapter 40. Chapter 40, really, guys, it's impossible. You really have to work on it. It's hard to go through all these strange shapes and stuff over Google Hangouts. But I'm confident if people, the website page is really good. But you want to keep your eye on the prize. What we're trying to figure out. So he's come to something very, he's developed a lot of important ideas. He's actually, might not seem like it at the beginning, rid himself of assumptions by the end of part 3. And part 4, we're going to go back to Mars. Apply all of this to Mars. So I'm going to end there. And yeah, this took a little bit long, but let's see if people have any questions. No, we have this call at 9, but people have any questions or things to say. And I do want to add, I'm definitely available if anybody wants to get on Google Hangouts or anything and just do with questions or anything about part 3, what we've covered the past 2 weeks. I'm definitely available to do that. So if you have questions now, that's fine, but if you're feeling at all overwhelmed or anything, I'm definitely open to getting on with people in the next week. But let's see if anyone has does anyone have any questions or things to say about part 3, about what covered today? Sorry if I scared people with the conchoid. It's pretty fun. It's a little bit funny. It also sort of comes as a shock when you're reading, but.
Well, I did have a question about attenuation, and but you answered my question. So, but thank you.
What was your question? Even if I answered it.
Well, because I was looking up what attenuation was in the first place, so I didn't understand, and I didn't understand really what Kepler was talking about. I don't know, I just didn't get it, and so I was trying to look at other physical examples, and what came up was a delta, like in a river. You have you have the strength of the river going out into the ocean, but it ends up, because it spreads out, ends up losing its power.
Right.
And basically, you connected the dots to what Kepler was talking about and what I had read about the delta. So.
No, that's true. And actually, you know, as I said, in chapter, what is it? Chapter 38. I mean, he's talking about water. You know, he's talking about he's talking about attenuation of the power of the sun. And chapter 38, one of the last analogy he uses is this combined cause of the sun, which is the rapid torrent, and the Earth having this ferryman on it. But so it is a good way to think about it, and a correct example. How in between the sun and the Earth, what happens to that rapid torrent? How does it dissipate? How does it weaken? But of course, as we've discussed, he also knows, I mean, really, I think he brought up the case of light, because he knows that this is a power which is not attenuating. If it were water, or if it were an odor, or something like this, it would weaken much more rapidly, right? It is a power which is acting across. That would be a pretty rapid torrent if it was just water, you know, acting across that distance, that kind of distance, and still having some force to it. But yeah, so you're right. And he used that water example with the sun. Anyhow, this chapter 40 part is hard, but that's another thing with the homework, is since nobody actually really answered the chapter 40 homework questions. I mean, I didn't really know where any of you guys were coming from in terms of having a sense of that chapter. But as I said, go ahead.
Well, here in Seattle, we haven't actually worked through 40 yet, because we didn't have enough time the last 2 sessions we worked on it.
Right.
But we were going to do it last night, but Pat Ruckert had a class, and so we ended up doing that, and it went really late. So we were going to do that, start that tonight, and then move on to.
Okay, great. And as I said, the benefit there is the web page. I mean, I tried to sort of add some of my own thoughts to it that maybe aren't explicitly there, but the web page is very thorough, taken together with I would suggest actually reading the chapter. You know, you'll get an idea of it. But yeah, that's fair. And if anybody wants to talk about this in the next couple of days, in the next week, before we start part 4, I'm open to it. And again, if I mentioned the essay questions, but if people can take the time to actually do the homework, it really is going to, especially even getting back to this kind of reasoning in chapter 40, it is really going to help for part 4. And I think Jason will he'll at least remind you of it. But doing some of the homework questions, there were 2 homework questions on chapter 40. I think it will help people. There were actually 3, because there was the mean, the one defining the mean equated in centric anomalies, even though I showed you where they were already. But it'll help you concretize some ideas from part 3 that will be important as we go forward. So I'll accept late homework.
Hey, Megan.
Yeah?
We were reading, when we got to this chapter on magnetism, I was unclear in my mind how he talks about the solar iron filings, how they're circular.
Yeah.
And how that's supposed to have a kind of circular orbital trajectory, and didn't really understand how that would work, if they're just fall up inside where they are in the sun. And then also, just as he's talking about this idea of the rotation of the sun at the equator and how this, that you'd have the planets spinning and revolving and orbiting at the same direction.
Yeah.
I mean, it's pretty wild to think about the implications of that for galaxies, things like that.
Yeah. Yeah, on the filaments, I think he obviously didn't know. He was trying to think about, he didn't really know how they were organized. I think one, and I actually can't remember everything he said, but I had read something that said, Gilbert, with what Gilbert had figured out about the compass and the Earth's axis, like aligning themselves, or, being able to act on one another, that, for example, if some of them were, some of these filaments were sort of parallel to the solar equator, and then you could imagine maybe there were filaments similarly situated in the Earth that they could act on one another. Gilbert had showed that magnets could act in a parallel fashion like that. So this is something I read somebody saying, how maybe what Gilbert had figured out, how was Kepler incorporating it into what he thought. I forget some of the specifics of how he says they might be organized and how the filaments might be organized in chapter 34, but I mean, I think he does not know. He's somewhat what he's doing with his magnetism thing is he's figuring out, and certainly he can't. He's not in a position to prove it, but he could say, well, based on the motion that I'm trying to account for, and if the sun were magnetic and if the Earth were magnetic, I could imagine that the filaments could be organized in such a way that they could act on one another. And on the rotation, I wanted to look at when we actually determined that, because it seemed like he was actually almost doing a proof that the base, it seemed to me like he was almost doing a proof that the sun rotates. I don't know when we actually, what he was saying, what he thought the period could be. I meant to look when we actually determined that for sure. Anyhow, it's quite interesting, and I mean, in terms of what you said about, I don't know what you were thinking about implications for that and galaxies. I was just thinking that just this thing with the heliosphere. I think I was thinking how excited Kepler would be if he saw that image of the heliosphere, which is quite vast in its extent.
Imagine how perplexed he would be if he knew the polar axis of Neptune is horizontal.
I know. Well, I still think that is very true. I think we have a 21st century article on it, which I've always meant to read. That is pretty interesting. Yeah, that might be one of those things where if he knew that, he would question himself. All right. Anything else? We have this call in a couple minutes. But yeah, please, if you can get time, I know there were scheduling challenges and other things, but it is a significant. There was a lot of material to work through, so even just because of course the homework is not graded. People know it's for your own comprehension. So if people get a chance to do any of it, I'll make sure to review it and get back to people, because you want to get clear on as much as you can before starting part 4. And people can call me or email me, or can do a Google Hangout, private Google Hangout, if people want to go over any of this. And I'll send out, like I did last time, I'll send out this PowerPoint I used so people can sort of look through it as notes if you didn't catch everything. I'll send that out. So, should we call it a night here? Well, I'm not calling it a night yet, but calling it a night for Kepler. Or at least this Kepler class. Okay, well, I had fun working through part 3 again.
Thank
Hope
you.
you guys had fun. All right, so we can be in touch. Definitely be in touch, and hopefully I'll get some more homeworks in.
Okay, thank you.
Bye-bye. All right, talk soon.
Bye.